All right, we are recording now. I guess it's time to go on and get started. I mean, way past time, I realized, but I was just seeing if any other students were going to come in. No other questions or issues before we get started today. All right, and most of what we have to do is with this, what do they call these things? My brain's going dead on the direction fields, and things that are leading up to the direction field. For instance, these, and I can't think what they call this one either, the phase portrait. So we're still dealing with phase portraits and mixing them in with direction field some. So let's, we're at the bottom of, if you got a book on Chapter 2, First Order Differential Equations, 2.1, Solutions Curves with no solutions, without a solution, and then page 42, the bottom of the page, we're going to be talking about attractors and repellers. And we kind of did this a little bit before, though I didn't give it those names. Let me... That's not what I want. Hey, here's what I want. Sorry. We go to our whiteboard. All right. Now, I'm going to try to do a couple things. You probably can't see this. You don't see a taskbar at the top or bottom, do you? You just see a whiteboard? Okay. Well, there is a taskbar at the top, which of course gets in the way, so I'm going to move it as far as I can out of the way. And then there's one at the bottom that also gets in the way, and I'm going to move it as far as possible out of the way. Okay. Now, so let's start going on that. Here's the, if there's no more questions, here's the supposition. Suppose that y of x is a non-constant solution of an autonomous differential equations. Now you remember, as we just sort of talked about, there are some constant solutions, okay, that are just pretty obvious. That is a solution, okay? But let's suppose that we have some that are non-constant solutions, okay? And C is one of the critical points of that differential equation. There are basically three types of behavior that y of x can exhibit near C, okay? And their picture on the side, that figure basically says it all. And I guess the best thing is to try to draw those figures like they have them there in the book. Now, do all of you have your text? I can't remember. Is anyone without a text? I know, Melissa, you have one, right?
Yes, sir.
And Billy, you have a text?
Yes, sir.
And Dawson? Dawson, you have a text?
Yep.
Yep. And Cole?
Yes, sir.
Oh, you do? Okay, so all of you do have text. So I don't have to draw them. I'll just show you what I'm talking about. Okay? And this doesn't come out well, but there it is. You see that in the text, right? And your C's there, the blue C's in the middle, are your critical values. Okay? Now, of course, these are Y's. This is autonomous, so all of it is Y dependent, not X dependent. Now, I mean, X's are involved, but it doesn't depend on X. So the blues are that. Now, the question is, what happens above or below that C? You know, what is going on there? And I think as you saw the in this, I don't know if you can make it out in the figure, but you got your book in front of you. Oops. There it is. Okay. You got your book in front of you. See, on the A part there, the little arrows are indicating that from C, you're going away from C in both cases. In B, you're going to C from below and away from C above. If I'm reading them right, it's hard to see in this little screen. And then D, I can't tell what D's doing. Okay, D, in A, they're both going towards C. In B, oh no, in B, they're both going away from C. In C, they're both going upward. Okay, one's going towards C and one's going away. And in D, they're both going downward. Okay, now, why they use these terms, I'm not sure, and I'm not even sure what difference it makes. I'm sure it must somewhere. But these are called, the critical point C in A is an attractor because both above and below you're coming toward A. Now, of course, what you know already, your curves are coming down, and since there's nothing above them, they're coming down from high and then asymptotically approaching C. And from below, they're coming up from way below and asymptotically approaching C. So they're attracting, C is attracting them in both directions. Now in B, C is repelling in both directions. Okay, so that means they were near C, asymptotically C, and going away from C above and going away below. So those are called repellers. It's a repeller in C. C, the critical point is a repeller in B. I'm sorry, I said C. Okay, now they're called semi-stable in the other. When they're both on the up and up or the down and down, you're stable in one direction and unstable in the other direction. The repellers are what they call unstable, and the attractors are what they call stable. As you go further along, you're reaching some sort of equilibrium, or you're going further from equilibrium. So when you're semi-stable, from one direction, you're reaching an equilibrium, the other direction, you're not. So that's what they're talking about. And when they talk about equilibrium, or I use the term equilibrium, they use stability. They're saying asymptotically stable. In other words, they are approaching some value as you go. And they go into that in more detail and then talk about the semi-stable state. Okay. Now, this would be the figure 2.110 on the side of the page there. I don't know if you can see it in this little figure. I can barely see it. That's obviously what they call unstable because in both directions.
Cutting out.
Say again? You can't hear me?
Professor, you're cutting out.
Okay. And that's because the book's in front of the microphone, because the microphone's the same place the camera is. And when I hold it up so you can see the book, you can't hear me. Okay? So I'll just let you look at that, and you see in both directions you're going away from C, from the left, from above, and from below. So that was what they called an unstable situation, or repellers. Okay. Asymptotically unstable, coming from stability but moving toward instability. Okay. And that's how you draw these in the direction fields. I think we did direction fields earlier, and then we got away from direction fields, and now we're coming back to direction fields. Now, what if you have two critical values, two or more, okay? And the next example shows this. I'll hold the picture up so you'll know where I'm talking about. It's that one, and I know I'm probably going to cut out here because the book's in the way, but that one. Now, obviously, at the bottom, y is equal to 0. That's a repeller, okay? Because they're going away. Going away as you increase in x, you're going more and more unstable. However, y is equal to 3, the upper critical value there, both of them are approaching. So that's a stable critical value, okay? And you can have lots of different variations on the theme there. Just depends on which way the arrow's pointing, in your direction fields. And frankly, I mean, I'm trying to cover this in case you ever need it again, but I can easily imagine, are any of you future mechanical engineers? Not? Well, I can imagine several situations you might want to find out does this situation produce a stable equilibrium? And if you got repellers there, probably not. Okay, if you have attractors, yes. Semi-stable, you might want to avoid those too, because they might be okay in one direction but not in the other. Okay. I can probably imagine some in electrical engineering as well. Seems like, certain circuits you want to make sure they are stable and don't start doing wacky things. I can't think of any particular example of that now. Industrial engineering, that would be a very important one to have stable situation. You don't want some portion of your manufacturing process to get out of control, okay, and to start doing flaky things. So I would think in most fields of engineering, you probably are going to run into this maybe just a little bit, some more than others. Now, they highlight a word here, and that's translation property. It's a green, bold, capitalized subtopic on page 43, and then they bold it again later on. The following translation property of an autonomous differential equation should make sense. If your y of x, that's your function, is a solution of an autonomous differential equation, dy dx is equal to f of y, then y1 of x equals y of x minus k, where k is also a constant, that's also a solution. And basically that's saying almost the same thing that we did before, our good old friends integration, which is a form of differential equations too, but there your one and only variable is your dependent variable. Now your one and only is your independent variable, but in a dependent variable, you have a family of curves, and depending on which, you just add a c to it and you get another one. Okay, so in this case, you have a family of curves, but you add the there it is. You add the constant to the y value, which is what you were doing before in a family of curves in y as a function of x, and you're integrating that, and you have plus c's. That translates the y's up and down. Okay, but when you're having your y is in your autonomous equation, that's your only variable, then it's the y that you're adding the k to. It's the x that you're adding your k to. I'm saying it backwards. You're adding the x to the k, so that gives you not a vertical translations of your curves, but it gives you a horizontal translation of the curves. And that's what that figure was trying to show, that any of those curves, if the red curve was a possibility, then the second red curve would be. If the purple curve, one of the purple curves was, the next one. You're doing a horizontal translation, x minus k. If the green curve was a solution, then the next green curve was a solution. You have a whole family of solutions with horizontal translations rather than vertical translations. So that's why they call it a translation property. Okay, your arrows and your direction fields indicate that's got to be repetitive like that.
Professor Tyler?
Yes.
Would it help, I'm not sure if this will resolve the issue with the microphone thing. Would it help if I email you a PDF copy of the book So you can have your book copy in front of you, and then if you need to show us a diagram, you can screen share the book onto
Okay.
your computer.
Well, now the only thing that pops into my mind, and this is not said in any critical way whatsoever,
Yes, sir.
but is that legal? I mean, the book I'm teaching from it, all like this, so I would think it would be, but
Yes, sir. So we have kind of like a PDF book library. I know like a lot of bookstores. Auburn has done it too, for where since we're transitioning to social distancing, a lot of PDF books have become available.
uh-huh.
So I can send you a PDF of it just to keep on your like Adobe PDF reader,
Okay.
and you can I don't know if that would make it easier or
Okay. Uh, okay. Now I'm trying to think if they loaded that on this computer. This is the school's computer, and I don't know for sure. Is that a free Adobe or is that a paid Adobe?
it's free, so you can
Free.
open it even
Okay.
you can even open it in your web browser.
Okay. All right. Well then, I know my wife has the paid Adobe version, so she could receive it, and but then whether I could use it, I'm not sure. But yeah, you can try doing that, and we'll do that. But and that way you'll all get to see it. Do most of the rest of you have PDF versions, or do you have some type of paper copy of a book?
I have the PDF version.
Oh, okay, good. Yeah, I knew that in some of the other classes, when students didn't have a book, another student would say, "Well, I'll send you a PDF," you know. And I thought, okay, I'm not going to say anything, but when I'm involved, I figured I needed to say something. But anyway, thank you. That probably would be beneficial. Okay, yeah.
I have an online copy that I have from like Cengage Unlimited.
Uh
But I
huh.
like to download them as a PDF because they match up better. So the PDF actually has the page numbers
Uh huh.
and looks almost exactly like the paper copy. So
Right.
it's easier to follow along with.
Right. Well, that was actually the model I was thinking in my head. If the, Cengage, I know they want their $119 from every student who has it. I'm not a student; they give me the free book, so I'm would be less worried about it for myself. But yeah, if that's something that say Auburn's and other places have done, sounds good to me. Thank you. At the very bottom of the page, they have a differential equation. Now I'm trying to see if there's any real benefit to talking about it. I guess it might be. So if y of x is a solution of an initial value problem, dy dx is equal to f of y. That's an autonomous equation, okay? And you know that y at 0 was y0, okay? So let me get my fancy little pen here to working. So here we have your differential equation, dy dx. These are pretty ugly d's sometimes, most of the time. Okay, is equal to some f of y, autonomous differential equation, not an f of x, so you can't do just the integration of it. And it's an initial value problem, so you do know that y of some point, it doesn't have to be 0. To me, initial means 0, but it doesn't have to be. Y at some value is some fixed value of y. So some fixed value of x is some other fixed value of y, and we're going to call that y sub 0. Clever name for it. Okay. Then, if that is a solution, then y1 of x, and they don't tell you where this comes from, but here's this y1 of x, some other equation, and this is also a function of x, Wait, it should be a function of, yeah, well, there can't. It's a function of x. So y can be a function of x, but the dy dx is only a function of y. So don't get those two concepts confused. Y is a function of x. Okay? And this y1 of x is also is equal to y of x minus x0. Now, I kind of don't like their terminology here because somehow, at least in my sick little mind, I would be tempted to relate this x0 to that y0. It's not related at all. This is just another x, a fixed x somewhere else. I don't like that they use the same subscripts here. It has nothing to do with the y0 at all. Okay. Shouldn't anyway. Okay. Because the x value that goes with this y0 is 0. And if that's the case, this would be 0, and that wouldn't make it a lot of sense at all. Okay. Now, what the translation property says is that this situation here tells you that this is also a solution for the, okay, I'm sorry. Here's why they put the x0 in there. Is a solution for a different initial value problem. See, this is your initial condition of that one. Okay? It comes up with some y value, y of x. Okay? That's the solution for the top one. Okay? Now, if you have this other function here, y1 of x is equal to y, same y you had up here, but evaluated at a different x. X has been translated right or left, depending on the sign of this. Remember, anytime you're dealing with x's, you go in the opposite direction of the sign. X minus x0, if x0 is a positive number, you're translating to the right. X minus, if x is 0 is a negative number, you're translating to the left. It's kind of backwards. The x's are always backwards. Okay, now, that this is a solution to this slightly different initial value problem. dy dx, wish I could just copy and paste. They don't give me that capability here. Okay, is equal to, very similar to the other one, but with a different initial condition. That's equal to your f of y, the same f of y, even though it looks like a much sicker f of y. That's the same f of y as above. Okay, same same differential equation, but with a different initial value. Now your y at x0, this thing that you had here, that translation value, this then gives you, that's ugly. Okay? This now is equal to your y0. Same y answer, but a different x answer. Now, if you think back to translations in what you did in pre-calculus algebra, that's exactly what you're doing here. You just shifted your function x0 units to the right if that was positive, or to the left if it was negative. Okay? That's all you did. And this is just saying your initial value went x0 units to the right if x is positive, and x0 units to the left if x is negative. And that's exactly all you've done. And that's what those figures were illustrating above. Okay? So, as an example of that, they say it's easy to verify that if y of x is equal to e to the x. Okay, let's just go here and say your y of x, that's a pretty ugly y, isn't it? Your function y of x is equal to e to the x. Okay? if that's your solution, that's good. I'm not going to write the interval, all real numbers x's, the entire real number line. That's your solution for the initial value problem, dy dx. This is the solution for dy dx. I wish there was an easier way to do that. I probably should do y prime, but they're doing dy dx. I'll do that if I could write a d. The bottom d's always give me a problem. The top d's are fine, but are better. Okay, this equation is equal to y, right? When y of 0, initial condition, y of 0 is equal to 1. Okay, easy to verify, right? If y is e to the x, take the derivative of y, e to the x. Those two are equal, and especially they're equal when y of 0 is equal to 1. You really should say plus c or whatever, but when y is 0, y at 0, when x is equal to 0, y is equal to 1. Okay, so there is your solution. Okay, now let's come down here and say we have same differential equation, just like we did before, dy dx that d turned out a little better. Dy dx is equal to y, same differential equation. I said that. Oh, goodness, ugly y. These came out all right, but the y sure didn't. Okay? But different initial condition. Y at 5 is equal to 1. Okay? Okay? What you see here, different initial condition, and what this thing up here tells us, if you had same differential equation with a similar initial condition, the only difference being you've translated the x value so many units right or left, then this should produce a solution. If this was a solution for this one, then you do y, and can I just leave off the of x? Y is equal to e to the, and then this would be x minus 5. 5s are kind of tough. Okay, x minus 5. That would be your solution to this one. Okay, if that's your solution to this one, which we show it is, pretty easy to verify, and then this one with y of, well, go back and do it, okay? Dy dx would be, if this is your y, dy dx would be e to the x minus 5, okay? It's the same thing, okay? No chain rule involved or anything else, and sure enough, those are equal, but now y at 5 has to be equal to 1, so when x is equal to 5, sure enough, you put a 5 in here, this becomes a 0, e to the 0 is 1. So yeah, that works. And you see it's simple example illustrating this. If you translate your x value in your initial value, that initial x, whatever that happens to be, translate that, just translate it in the form down here. Do a minus x0 here, and you get it. Now, why they threw that in at the end, possibly you'll have lots of applications for it. They didn't do an example. They did nothing else. But anyway, we finally, thank goodness, finished 2.1. Now, homework exercises, I think I've given most of these before. Do either 1 or 3 if they're in the back of the book. They draw the direction fields for you, so you don't have to do that. Then do any of the odds 5 through 11. They, if those are in the back, do any of those. Do number 13 if it's in the back, and do number 15 if it's in the back. If you find the discussion problems in the back, take a look at those as well. Most of the time they're not. All right, now number 17, I'm really hesitant to even mention that, comes up with a new term in bold, a nullcline, as opposed to an isocline, which, if you want to pursue that, you can, but that's up to you, okay? Section 2.1.2, that's the one we've been in now for a couple of days. Number 19, if that's in the back of the book, any of the odds 21 to 27 if they're in the back, and 29 if it's in the back, okay? And then again, the discussion problems, if any of those are in the back, you can take a look at them if you'd like. They have another bold term there, and that's isolated. A critical point C in an autonomous first-order differential equation is said to be isolated if there exists some open interval that contains C but no other critical point. So that, to me, is a pretty vague definition, but maybe it makes more sense than what it was. There are other models now you can look at. The population model, we saw Malthus's model. This is sort of a modification of that. That's actually 38, so you wouldn't have that. 39, another population model that is a modification. Terminal velocity, we talked about that before. Chemical reactions, we talked about those before. So I don't think there's anything new there, just going back to those models that we had. But now we're ready, thank goodness, for section 2.2. We're finally going to start solving some differential equations. Not verifying they are solutions, not looking at how solutions are related to one another, but actually solving differential equations. We're going to start with my favorite because they're the easiest, but they're also fun. They're the separable differential equations. Now, let's jump back to something a little bit easier. And here's where we're heading. Okay, I'm going to clear it. Does anyone need this screen any longer? If you really like looking at hieroglyphics, you may, but otherwise, I don't see why you would. Okay, so let's clear that out of the way. And now I also have this box that shows, you probably can't see it, my name and all your names and stuff like this. I'm going to try to get that as far out of the way. Not all your names, it just says my picture, ugly, and then 3 names. I'm going to get that out of the way. A first-order differential equation that is not autonomous, okay, would be like this then. dy dx that bottom D just has problems, doesn't it? dy dx is now some function. If it's not autonomous, in general, it may be a function of both x and y. Nothing to keep it from being. This is the equation, the expression on the other side of the equal sign from that differential equation. Remember in the very first, when we started looking at these, what was the one? 0.1, oh, I don't know, something about e to the xy, or e to the point, it has x's and y's in it. Any function that has x's and y's in it, okay? We're not quite going there yet. That's where we're heading, okay? What if this one didn't depend on y any? If it didn't depend on x, that's autonomous. We've already talked about those. But if it doesn't depend on y any, this takes us basically back to Cal 2, doesn't it? Then you would just have dy dx is equal to some function of x alone, okay? Before autonomous was y alone, now it's just x alone. Well, this basically is what you did, sort of did, probably did in Cal 2. Okay? Now, most pure mathematicians would scream to hear me say it, but it's sort of like you multiply both sides of the equation by dx. That's not what you're doing. You're writing this in differential form. In differential form, this would be dy is equal to f of x. Easy to say, not so hard, easy to write. Dx, written in differential form. And then what would you do to that? You'd integrate both sides. And generally, this would be, without any other information, this would be an indefinite integral. Well, fundamental theorem of calculus, I think it's the second part, or however you, different books call it different things. This means this is just your y here on this side. And over here is whatever that integration produces. And if it's an indefinite integral, it'll be a plus c at the end, because any constant will also make that work. Okay? And usually in Cal 2, they would call that antiderivative of f, capital F of x plus c. Always would have that constant unless you had an initial condition or you had a definite integral somehow. Okay? So we know how to do that. That's solved by integration. Now, I'm sorry. I used a different nomenclature than they did. I shouldn't have. I wondered about it myself because that I hated using the x again. I just didn't notice they didn't use, f again. This was some g of x. And that I need to erase it here. And probably change this to a capital G of x here too. I don't think the book does that, but I was just trying to draw you back into reminiscent about your good old days in Cal 2, which I'm teaching this term, so that's why I remember it so well. Okay, and that's exactly the terminology they use, where G of x, capital G of x, is the antiderivative of the indefinite integral of G of x. Now, I guess they're just wanting us to do a couple, so let's do it. Here's a dy dx over here. Let's see if I can write it again without too much problem. There's always problems. Everybody's got problems. Dy dx. I have a niece, and that's one of her favorite sayings. Everybody's got problems. Okay, is equal to, where is it? 1 plus e to the 2x. 1 plus e to the 2x. Okay, there's your differential equation. The right-hand side is a function of x alone, no y's messing it up any. Okay, so what would its solution be? Well, you don't have to write it all out. You can just take an antiderivative right there. What's the antiderivative of 1? dx, by the way. Anybody? This would have a solution. I'm trying to skip steps because it just takes me so long to write them. Antiderivative of 1?
X.
X, you got it. Antiderivative of e to the 2x?
E to the, wait, E to the 2x.
Okay, it's certainly going to have an e to the 2x in it. But it's also going to have a kind of a anti-chain rule type thing. You would have to precede that by 1/2, wouldn't you? Or put it over 2. Okay? Now, before we go any further, I know there's a plus c after it. Let's take a derivative and see if indeed we get that. let's verify it, okay? Derivative of x is 1. Derivative of e to the 2x is e to the 2x times 2, so that's why you need the 1/2 there. Does that make sense? So since that works, then all you have to do is put a plus c here. Now they do is a little c, mine up top look like a capital C. I don't care what size C you use or any other letter, not an E or an X, okay? Or a Y, you know, just use some letter, doesn't matter which, okay? So there is your solution. They write it as y is equal to x plus 1/2 e to the 2x plus c. And so it's 1/2 e to the 2x, takes more writing than e to the 2x over 2. I'm going to leave it that way. Okay. Now, here comes the definition. Y'all have your book, so let's not get carried away here. You have your books, you can see it. That equation, the one that's e to the, this one right up here, dy dx is equal to g to the x, okay? As well as its method of solution is just a special case of when a function f is in normal form. Remember what normal form is? If it's a first order differential equation, you have your dy dx on this side and your f of xy on this side. That's a normal form. This would be if it's a normal form with no y dependence in the f. Then it would just be a g. Okay, now, here is what we're going to be talking about in separable equations. If this f of xy is not just a function of x alone, which we just did here by integration, or y alone, which we did by autonomous means, but what if it's a function of x and y, but a very special function of x and y, a product of a function of f times a function of y, a function of x times a function of y. If that's the case, the first order differential equation of that form, now forget about, well, no, they're going to keep the same concept here. So here's the form we're talking about. dy dx, normal form here, right? The derivative on this side, and this is the first order, dy dx. That bottom x is just pathetic, isn't it? dy dx is equal to some g of x times h of y. If you can figure out some way to write that f function up here as a product function that's strictly x's times something that's strictly in y's. If you can figure out a way to do that, guess what? You've got it knocked. That's what we call a separable differential equation. And if you have one of these are pretty easy to deal with too. Okay? I want to jump right into showing you how to deal with them, but I guess we'll have to. So we either say these are separable or separable variables. Said to have separable variables. You can separate the variables. So let's take a look at a few examples of those. Excuse me, I got hiccups now. Here's one. dy dx is equal to y squared x e to the 3x, that's supposed to be a 3, that's supposed to be an x, that's a pretty ugly x, okay? 3x plus 4y. Okay? Wait a minute. Wait, time out. That's not a product. That's a sum. That's not separable, is it? Any help on this?
You can factor it, can't you?
Well, I guess factoring is one word you can say for it. A product of exponents. If you have a sum of two exponents of the same base, a to the b plus c, that's the same as a to the b times a to the c, right? Yeah, let's do it that way. If that's what you meant by factoring, that's exactly right. This would be a y squared x, and you can rewrite this e to the 3x plus 4y, that's looking more like a t all the time. You could write that as e to the 3x, and the 3's aren't getting much better. X got a little bit better, times e to the 4y. That's a property of exponents. I hope you remember that. I mean, think in just general terms. What if you have 2 to the 3rd plus 7th? Okay? Well, 3 plus 7 is 10. Well, 2 to the 10th, I don't know what that is, but that's the same as 2 to the 3 times 2 to the 10th, right? When you're multiplying bases, same bases, different exponents, keep the base, add the exponents, okay? Get it a little simpler numbers. 2 cubed, 2 raised to the 2 plus 3. 2 plus 3 is 5. 2 to the 5th power is 32. Well, that's 2 to the 2nd, which is 4, times 2 to the 3rd, which is 8. Yeah, that's 32. So sure, this is a principle of exponents. You can split them. Now you see here's a function of x, and these two multiplied together give you a function of y. Those two are multiplied together. Sure enough, this is separable. Now that'd be sort of a pain in the neck separable equation to do, but it's doable. And it's not really that bad. It's just integration by parts for each one of them, but we haven't gotten there yet. Okay? Now, how about this one? Now, even though they had a sum in it, it could still be written as a product. And here it is. This is a product of x's, and these two are products of y. Is a product of y. So how about this one? dy dx. Let's see if these will come out anywhere close. That's supposed to be a dy dx. Okay, is equal to y plus sine x. What you think, separable or not? No way in the world you can separate those into products of two functions. That's the sum of two functions. This you can get the sum into a product using the principle of logarithms. The principle of exponents. This one, no rule here whatsoever that will ever make that a product. So this one's separable, even though it's a pretty complicated looking thing. This one's not separable, even though that's a little bit easier. Now, there are ways to do this, but they're not by separation of variables. Okay? So, that's the deal. So, we've seen what these are, and by the way, on the next page, they rewrite this one. If I can find my cursor, there it is. Okay? They rewrite this one just like I did below, but they write them together. I think they put the x's first, don't they? Yeah. The first function would be x e to the 3x that's the first function. The second function would be y squared e to the 4y. And that's a product of function of x alone times a function of y alone. This would be your g of x from here. This would be your h of x from there. Okay, so far they've just shown you what these look like. Okay, well, how in the world are you going to go about solving that then? Now, by the way, and then the second equation, you cannot write it as, there's no way of expressing y plus sine x as a function of, as a product of functions of x and y. Okay. Now, they head off into a really complicated way of doing this. And it's perfectly fine, and I'm going to encourage you to read this, and if it makes sense to you, by all means follow it. Do whatever it takes. Let me show you what I consider the easy way of doing this, okay? And maybe they get around to doing it. Yeah, they finally do. But they jumped through so many hoops and introduced new functions, fees and phi primes, and all sorts of things there. And so far, I haven't figured out why they do that. Okay, there may be some really good mathematical reason why you do it. Here's the bottom line: get all your x's on one side and all your y's on the other. So basically, write this in differential form, your dy dx. Put the dy over here, move the dx over here. And then get the y functions back here with the dy's and leave the x functions with the dx's. Okay? So if it's okay with you, I'm going to erase this step down here because it's in my way. Okay? And tell you what I'm just saying. Now, if I'm skipping too many steps, part of it is because I'm lazy, but the other part is writing. This is such a pain. So let's first just imagine you've taken the dx here, moved it over here. Okay? Then the next step is divide both sides by this function of y. So what you have now is dy, that stayed on the left-hand side. And when you divide it by this, that is divided by y squared e to the 4y. Okay? That's a pretty ugly y. And on the right-hand side, what you have is an x e to the 3x. That was your g function from before, remember? And then you have your dx you moved over here. Now, at this point, what I do, integrate both sides. That's a pretty ugly integral sign. Maybe a little better, but not still very pretty. Okay. This side here is something that can be done by integration by parts. Not bad. This one over here, that is a bear and a half. Okay. In fact, just looking at it, I can't think of any easy technique to solve that. But guess what? They're not going to try to solve that. They just say, get all your x's on one side, all your y's on the other. And then you integrate. Whereas before, up here, when it was just a function of x, you just integrated the function of x. Now you're going, and over here, remember, all we did was say the integral of this, up here. The integral of dy is always y. Integral of g of x dx is some capital G of x plus c. Well, same thing down here, only wherever my cursor is, there it is. Down here, you have to integrate this side. It's not just an easy thing like this. You actually integrate. And you integrate here too. Now, guess what? You don't need a constant of integration on both sides. Most of the time, they reserve that to the right-hand side. Doesn't matter which side you put it on. It's just a constant. You can put it anywhere you want to on either side of the equation. but you don't need to do a separate constant of integration for each one. One will cover them both. Okay? This I wouldn't want to try to do in this class. Okay? This one, that wouldn't be too bad. It would take a little effort, but not too bad at all. Okay. And I hope they're not going to give us that. And that's their note there, is there's no need to use two constants of integration and separable. Just write your answer to first, h of y equal g of y plus c. Just put it as one constant. So, enough of the blah, blah, blahs. Let's actually go around and solve one. One that's a little easier than their first example. And it wasn't really an example, it was just out there. Here's example 1, and here's how it looks. 1 plus x. Now this one's written already in differential form. dy, which is a fine way to write a differential equation in differential form. Doesn't have to be in derivative form. No, yeah. Minus, I wrote it wrong. That's not an equal sign. I misread it. That's a minus sign. Well, wrong one erased, but that's okay. Okay. Minus y dx is equal to 0. Okay. Now, does that look like potentially a separable differential equation? You got x's with the dy's and you got y's with the dx's. So that isn't quite what we had in mind, is it? Well, it's pretty easy to rectify. Let's just add the y dx to both sides. And that would then become, I'm not going to show it, I normally would, but I'm not because it just takes extra writing. Your left-hand side stays 1 plus x dy. Whoa, that's a terrible x dy. Okay? When you add the y dx to the other side, that's equal to y dx. Any argument there? Any gripe or concern? Ooh, that's a terrible x too. X's aren't doing too well in this problem. Well, the problem is you got your dx and dy separated, but they're with the wrong variables. So basically what we do is divide both sides of the equation by 1 plus x. And when you divide it here, it'll go away. So I'm just going to wipe it out, not have to write it down. And it'll go over here because there's nothing to wipe it out here. 1 plus x. And we'll divide both sides of the equation by y, which will wipe it out here, and put it here. Okay? Now I have it written the way I should have, which I should have written 1 plus x here, wiped it out, the y here, and wiped it out, but it's just extra writing, and it's costing me a lot of angst. So I don't want to do it. So what is your differential equation now? dy over y is equal to dx over 1 plus x. Now you do have your variables separated completely. This is a y, by the way, okay? So what we do at this point? Integrate both sides. Undo your differential equation by integrating, okay? What is the antiderivative of dy over y?
Natural log of
You
y.
got it. Natural log of y. Okay. Now, next question. What's the antiderivative of 1 over x dx?
Natural log of x plus 1 or 1 plus x.
Just natural log of 1 plus x. Sounded like there was extra x in there. That's a pretty ugly x, but just average that one with this one up here, and they come out being fairly close to what an x should be. Okay, never mind. Okay, what are we missing?
Your constant.
Oh, yes, we need a constant. Now, does it have to be a c?
No.
No. Is this a constant? Is natural log of c a constant? As long as c is not 0 or negative, it is. Right? That's just a number. Natural log of a number is a number, as long as that number isn't a 0 or negative number. Now, I'm looking ahead into my murky crystal ball here because I think that's going to be more useful to us. Okay? Because what I'm going to do next is use a property of logarithms. We used a property of exponents before. Property of logarithm kind of undoes that one. If you have the sum of two logs, anyone remember what that is? Isn't that the log of the product? Anyone remember that rule?
Yes.
Yes, it is. That's it exactly. And this is equal to log y, right? Now, I'm cheating because I knew this. This is, you run into this a lot, and as you run into it, you learn to do this. Now that you've got pure logs on both sides, if you had a plus c out here, that's not a log, and you can't do what I want to do next. I want to exponentiate both sides. Raise both of these to the e. And what is e of log y?
Just y.
Just y. And what is e of log of c plus c times 1 plus x?
C times 1 plus x.
You got it. Now, I'm not sure they did that at this stage, but I'm just showing you a shortcut that you're going to run into a lot of times, and if you do, try to remember to write that constant as a log. Let's see if that's what they did. Okay. Now, I cheated in a couple ways here. And it's just that I was cutting steps. You really ought to put absolute value of y. Because y, if y is negative, you can't take the log of it. You can take the log of its absolute value. Same here. This shouldn't be parentheses. These should be absolute values. I've already said c is going to have to be greater than 0. Okay. And then when you do this, that will just give you your y. And c, okay. And they go through a lot of different ramifications here, and they do use a plus C1, they call it, and they know they're going to go back and do the other. I cut to the chase and eliminated a lot of those steps, and we came up with the same answer. And that's what they get. Y is equal to some constant c times 1 plus x. Now, if you didn't know to or didn't think about doing and just put a plus c at the end, which is fine, follow what the book did. It's a lot more involved than messy, but it comes out being exactly the same answer. This is the shortcut. And since I'm having to write with my finger, I'm going to take as many shortcuts as I can. Okay. Now, any questions on that? I admit I cut corners because I knew what corners to cut. They go into the same deal, and they say use your constant of integration as log the absolute value of c rather than c, and they go through the same way and basically come up the same way I did. But I thought, why show you the hard way and then show you, well, here's the easy way. Why don't I just show you the easy way to begin with? All right. Now, example 2 is going to be an initial value problem. This is not. This gives you a family of solutions for different c's. You get different solutions. So we'll just sort of leave that alone. They didn't do the graph, so I'm not about to either. So let's do example 2. Is it all right to erase this one, example 1, because I think we'll need more room for example 2. Anyone need this up a little bit longer? I can't imagine any of you could write more slowly than I do, so hopefully you've got it all. Any questions before I erase it? Okay. So let's go to example 2. Here's an initial value problem. dy dx goodness, they turn out so bad in the denominator, in the lower part, is equal to, this is written in normal form, minus x over y with the initial condition of y of 4, which doesn't seem very initial to me. It's supposed to be a y of 4 is equal to 3, I believe it. No, negative 3. Okay, so there's your initial condition. All right, first question is a separable. What do you think? What we want to do to have a separable thing is have your y's and dy's and everything with y in it on one side, and your x's and your dx's and everything with x in it on the other side, and having no mixture at all. Can this be done?
Yes.
Yes. What you do is multiply both sides of the equation by y, and this is the part that drives most pure mathematicians crazy. Multiply both sides of the equation by dx, or write it in differential form. So you could say, write this in differential form, dy is equal to minus x over y dx. That's in differential form, then multiply both sides of the equation by y. However you want to say it, it comes out y dy is equal to a minus x, ooh, that's ugly again, dx. Oh, that's even worse. That's supposed to be a d, folks. Can you live with it, or you want me to clean it up? Anybody? All right, to leave it, because the next thing I'm going to do is, guess what? Integrate both sides. And this time I'm going to try to get that minus sign outside the integral. What's the antiderivative of y dy?
1.
A. You're taking the derivative. I want the antiderivative.
Oh, y squared over 2.
And I'm going to have to talk with your Cal 2 instructor. Okay. Y squared over 2. I was as a Cal 2 instructor. Okay. We won't do the plus c on this side. We'll put it on the other side. And this will be what?
Negative x squared over 2.
You got it. Negative x squared over 2.
Plus c.
Now, I'm going to be lazy again if it's okay. Dawson's not used to me being lazy, are you? Okay. I'm not going to write that as c. Guess how I'm going to write it? as c over 2. I don't have to do that. I'm just doing it because I'm kind of lazy. Because guess what my next step is? Anybody?
Add them together.
Multiply everything by 2, right? Which, wah, wah, wah. Notice the sound effect? The 2's go away. And you're left with y squared. If I could write it, I guess I'm paying the price of being lazy, is equal to minus x squared plus c, right? Actually, I want to go back and change something. I want my constant to be c squared over 2. Is that anything wrong with that? If c is a constant, c squared is a constant, right?
Yeah.
Why would I want to do that?
Because then you have y squared plus x squared equals c squared.
Yes, only I'm going to write it as x squared plus y squared is equal to 0. It doesn't matter which way you write it. And what does that give you? You probably should have known this before, but definitely after Cal 3. What is that an equation for?
Circle.
Family of circles centered at the origin with radius c. And that's your constant. So it could be a little circle if it's c is a small number, a big circle if c is a large number, a huge circle. It would be 0. It would be a point if c is equal to 0. That would be the point 0, 0. That would be the only solution for that one. So sure enough, this is a family of concentric circles, all centered at the origin. Okay? There's your, except we have an initial condition. So let's put that initial condition in there. When x is equal to 4, this will be 4 squared plus y is equal to minus 3. I'll go on and write it that way. Minus 3 in parentheses squared, because that's what you're squaring, the negative 3. And that has to equal, and I chose to write c squared, and there's going to be a reason for it. Okay? And what's 4 squared?
16.
And what's negative 3 squared?
9.
And that's equal to? $25, and that should be your c squared, except I wrote it as a c, and nobody said anything. Speak up, okay? And that's equal to your c squared. Now the question is, what is c? Two possibilities. Say again?
Plus or minus 5.
Plus or minus 5, okay? And let's think about, I said it was a family of concentric circles. The issue with that is, that's not a function, is it? A circle is not a function because it fails the vertical line test. So it's a family of semicircles, either positive or negative, and since the point 4, negative 3 is on there, that means your x squared plus y squared is, let's see, how do I say this? It's the bottom half of a circle. Okay, if you want a function, it's the bottom half, because in the fourth quadrant is where x is positive and y is negative. So it's a circle of radius 5, okay, but you're down here, and to have a function, that would be the semicircle of radius 5 in the lower half. So, does that mean the c is negative? I don't think it quite matters, okay? Let's see what they say. What matters here is that if writing it as a function of y alone, you subtract x squared from both sides, so it doesn't matter if the c is plus or minus 5. That would be, you would say y squared is equal to 25 minus x squared, and then your y would be the negative square root of that. Negative the square root of 25 minus that. 25. No. Yeah, 25. That's supposed to be a 2, folks. 25 minus x squared. So the c doesn't matter which you call it, plus or minus. Doesn't matter in this case because you're always going to be dealing with c squared. That one I think I will erase because that's my final answer, and it looks so bad. And this will probably come out looking worse. It couldn't be much worse. Okay, there's your answer. The fact that this is a minus 3 here requires your y to be negative when x is positive. Okay, so that's the only way you'll get a negative y out of it. So the sign for c doesn't matter. C squared was 25, whichever your c was, so it's going to be the square root of 25 minus x squared, minus the square root of that. Now, remember also what we said before, anytime you give a solution, you really are supposed to also give its I'm trying to think of the name they call for it. Interval. It's interval of solution, basically. That's what they call it, interval of solution. And this will only be good from minus 5, because this is a semicircle, is less than, now I want to say strictly less than, and that's what the book says too, less than x, and it's strictly less than 5. Now, why didn't I do plus or minus 5? Because surely that would be on your circle, wouldn't it? Okay, it would, but if this were equal to either minus 5 or 5, what do you have in your denominator here then? I mean, in your radical? 25 minus 25, which is 0. And y would equal 0. But can y equal 0? No, it can't. In your initial problem, and we probably should have written this down, as soon as you see that y in the denominator there, you should have also said, comma, y cannot equal 0. Okay, and if y can't equal 0, that means the x can't equal plus 5 or minus 5, because both of those would produce a y of equal to 0. So your interval of integration, or interval of your differential equation, where it's valid, is only minus 5 to 5. Out there, outside those, it has no meaning at all. At 5 and 5, your y would be 0, which it can't be according to your initial differential equation. All right, does that make sense? Okay, and the figure in your book, I wouldn't even pretend to, well, actually, I could kind of draw it. Not really, but kind of. You got your book. There it is. Yeah, there it is. The whole family of circles would be those concentric circles. And the semicircle that contains the point 4, -3, over there in the fourth quadrant, that's the one that would identify as the semicircle of radius 5, the lower half, with open circles at the x-axis because y cannot equal 0. So graphically, you see y can't be 0 as well. Any questions on that? Now, the next little subtopic before you get to example 3 has a funny name to it, losing the solution. Have you lost the solution again? I mean, you need to keep up with these solutions, okay? Some care should be exercised in separating variables since the variable divisors could be 0 at a point. And if you think back of what we've been doing, we've been dividing just willy-nilly sometimes. That first example, remember, we divided both sides by y, example 1. And we divided both sides by 1 plus x. Well, what if x was equal to negative 1? What if y was equal to 0? Then those would not make any sense whatsoever. So we really should have, even though our initial differential equation would have allowed them, if x were negative 1, then the only way you could get that was for y to be equal to 0. So negative 1, 0 would be a solution for that differential equation that you wouldn't get from the one that we got. Or I don't, well, yeah, you still would. So sometimes you don't lose them, sometimes you do. So some care should be taken, blah, blah, blah. Specifically, if r is a 0 of the function h of y, then substituting y is equal to r into dy dx is equal to g of x, times h of y makes both sides equal to 0. In other words, y is equal to r is a constant solution of the differential equation. But after variables are separated and you do your thing with them, then the y might not show up as a family of solutions because you were dividing by something that ultimately became a 0 later, is basically what the deal is. So let's do example 3 and see if that makes sense. Now, yeah, what we got? About 12 minutes left? No, we got until 10:45. Sorry. Okay, so let's do. Can I erase what we've got here?
Yep.
Example 2. Okay, let's do example 3. Here's our differential equation. dy dx, written in what they call normal form. Ooh, that's an ugly d. Thought it was going to turn out okay, and it still come out ugly. Okay. dy dx is equal to y squared minus 4. This one you can almost smell what the problem is. Okay. Okay. Now, if you were just proceeding willy-nilly and had not talked about what we just talked about before, what would be your approach? Wouldn't it be, write this in differential form, in other words, put the dx over here, and then to get the y's on the other side, divide by y squared minus 4, right? Yay or nay? Now, this is not a initial value problem, so we're just going to go. So this would produce, now tell me if I'm wrong, we just proceeded, dy over y squared minus 4 is equal to dx. Yay or nay? Right? Okay. Hopefully y'all are saying yes. Nodding your heads, I just can't hear you rattle. Okay? So what we do Integrate both sides. That's a pretty ugly integral. This time I'll do the right-hand side. No, okay. Now, how would you do the left-hand side? Uh-oh, SpaghettiOs. Cal 2 all over again. Anyone remember? Please? I just want to check on something. All right, we've lost both of the gals. What did y'all guys do? Forget to put on deodorant this morning or something? The girls have left. Okay, never mind. I didn't say that. Okay. Just stuck with the two of you. I didn't say it that way either. How would you solve that left-hand integral? Anyone remember the technique?
You have to like separate them.
Okay. I think I know what you're saying there, and if this is what you mean, I'll agree with you to some extent. Make that integral dy over, when you say separate, meaning factor, say yes.
Yes.
Okay, y plus 2 times y minus 2, say yes. Y'all write a lot faster than I do, don't you? That's not saying much. Okay. Is that what you meant by separating them?
Yeah.
Yeah, okay. How would you proceed from here? Let me come down here and do it, and maybe you'll remember the name. I'm going to forget about the dy for now. I'm just going to look at the fraction part. That's part of the name. 1 over y plus 2 times y minus 2. Oops. Ooh, ugly. Okay. Now that fractional form, I'm going to hope, can be split again, and maybe this is what you meant, into some a. Is this ringing a bell yet?
Oh, yeah.
Oh, yeah. Okay, you better say that. Okay. Over y plus 2 plus some b. Anyone remember the name of this yet? Hint, fractions in the name. This was called the method of partial fractions. Okay? If we can find the a and b that makes that true, then we can go back and integrate that much more easily. In fact, we can't integrate it. We can't otherwise. Okay. So, what's your first step here? If that is indeed true, what is it you don't like about that problem?
You need a common denominator.
Yeah, you have denominators, and the common denominator is this one right here. So I'm going to multiply every term on both sides of the equation by that common denominator. And rather than write it out, I'm going to represent it as this times this. You fill in the x plus 2 times the x minus 2. I'll write it here as this. I think I probably have to write it here. Y plus 2 times y minus 2. I think to make it easier on the next one, I'm going to make it the parentheses, and this time inside the parentheses, I'm not going to write it all. I'm just going to write the plus and the minus, and let you fill in the y's and the 2's, okay? Now, I'll do the same here. That'll make it a little easier to see, maybe. That's the plus here and the minus here. You fill in the y and the 2. Well, here, y plus 2 goes out. Y minus 2 goes out. Here, y plus 2 goes out. And here, y minus 2 goes out. So what have we just done? We have reduced a fractional equation into an equation with no fractions, and don't we like that? Okay? And on the left-hand side here, all you're left with is a 1, because everything else went out. And over here, you have a times, I'll go and write it, y minus 2 whoa, that's ugly, plus b, I'll go in and fill in the blanks on this one too, y plus 2. Now here's the part that kind of drives me a little snaky, because I don't see how you can quite do it legally, and yet it works. So we'll do it anyway. This should be good for any values of y, right? So why don't we just let y equal 2? So if that's good for any, let's let y equal 2. Now what does this equation become then? 1 is equal to, when y is equal to 2, this goes to 0, so this whole term goes to 0, and you're left with b times, remember y is equal to 2, so that would be 2 plus 2 is 4. Didn't know you'd be doing such high-level math today, did you? Okay, and what does that imply? That b has to be equal to 1/4. Do you see that? If y is equal to 2, this goes to 0, meaning that whole term goes to 0, and this goes to 4, so you have 1 is equal to 4b, divide both sides by 4, and you get b is equal to 1/4. Okay? Then, since that works so easily, we'll choose the second one to be y is equal to, guess what?
-2.
-2. Perfect. And you do that, the left-hand side's still 1. That had no y dependence left because everything else went out. And this would then be -4 times a, because -2 minus 2 is -4a. And over here, this one went away. So you're done with that. So a is then equal to -1/4. That's supposed to be a minus sign. It's a pretty ugly one. Okay, -1/4. So now let's go back and do our left-hand side here. And that will now be, we're going to put the dy back in where it belonged. And that will be dy. I'm going to reverse the order here if you don't mind. Over, I'm going to put a 1/4 out front, because that was your b, is 1/4, over y minus 2, that's the one that went with the b, and then you had a -1/4. I'm skipping some steps here just because I hate writing with my finger, okay, and that would be dy. Oh, that's an ugly d again, isn't it? dy over y plus 2. Okay, and that's supposed to equal to, on the right-hand side, just x. The antiderivative of dx is x. Okay. I probably jumped the gun on doing that because I really should put a plus c out there, but I don't want to. I don't think yet. Okay. So what does this produce for us? You can factor 1/4 out of both of those. What's the antiderivative of dy over y minus 2? Anybody? We've hit it before today.
Maybe the ln of y
Yeah,
minus
that's it. The natural log of y minus 2. And again, now before I forgot to do this, so I'm going to do it this time. Put it in absolute value bars, y minus 2. Okay. I pulled out the 1/4, but I still have the minus sign here. What do you have here? The log of absolute value y
plus 2.
And that's equal to x. And I don't know whether to put a plus c there or a plus log c. I just don't know for sure which is going to work best. I need to close this parentheses because that 1/4 is out there in front of all that. And so let's equal x. And I don't know to do plus c or minus c. I mean plus c or log c. But I know the first thing I'm going to do probably is multiply both sides of the equation by 4. Okay? And then I'll use this property of logarithms that the difference of two logs is the log of their quotient. So that is going to be the log of y minus 2. And notice I'm sort of leaving off my absolute value bars. I probably should put them in. They're just hard to draw, so I'm going to let you put them in when you do the writing because I'm having trouble writing what I am. Okay. Really, let's just do it this way. Let's make that, rather than parentheses, make it absolute value. And that doesn't look much more like an absolute value, but let's just pretend it does. Okay. Now, this will be equal to 4x. I still haven't decided whether I want to do a log c or a c. Let me see. I think they just leave it a c. Yeah. So let's do plus c. Now they're going to call it a C1, and there's a reason for that. But because the subscripts are hard for me to write, I'm just going to leave it a C. Okay, guess what we're going to do to both sides then? Undo the log. E them, okay? Raise both sides as powers of E. Okay? You okay with that? And this gives you y minus 2. I really should do absolute value over y plus 2. That's supposed to be a y. Okay. Is equal to e to the, for some reason the pen's not writing, 4x plus c. Okay, except let's go back and use that property of exponents and make this a, rather than c, and that's why they did a c1 before, do an e to the c, make that your constant times e to the 4x. Now I know I skipped some steps there, and this c down here is not the same as that c up there. This is e to the c, okay? That's what this constant is. But that's ultimately I want it to be a c. So that's what that is. Now, that's still not the answer they have in the book. The reason they want to write it as a function of y, explicitly as a function of y, and these y's are not explicit. They're combined. So here's what we're going to do. We're going to multiply both sides of the equation by y plus 2, so that gives you y minus 2 is equal to y plus 2 in parentheses times, yuck, that came out ugly. Times your c e to the 4x. All right. Now, what we're going to do next is multiply this by both of these terms. So this gives you a c e to the 4x goodness gracious, this won't write. 4x times y plus 2c e to the 4x. Whoa, that's an ugly e. All right, this is so tiring. Now we're going to subtract this term from both sides. And basically I'll wipe it off of this side, and that has a y in it. I forgot to put my y there. Okay. And we'll add 2 to both sides. So this is going to have a plus 2 somewhere out here. Okay. Now, I'm out of room. And I think where I'll go to make some more room is up here. Y'all are through with this, right? Please say yes, because it's going away.
Yes.
Good, thank you. Okay. And I'm kind of wanting to do it all, so I think I'll do it all. This is so much fun too. With my ionizing pen, it was so much easier than my finger. But it is wiping it all out ultimately. It's just really painstaking. Okay. Let's go back to our drawing board. Okay. So if we can figure out what this equation down here says now, let's see if I can write it down. We have a y plus c e to the 4x times y. That's all that's left on this side because these two added to 0. And that's equal to a 2c e to the 4x plus 2. which I could factor out the 2, and I think I will in the next step. So that's all that's left down here. 2ce to the 4x plus 2, because this one we subtracted away. So let's factor out the y here. I think you can see where we're heading now. I hope so anyway. Factor out the y, and that leaves us in parentheses here 1. Now I'll put a plus sign here, and y'all let me get away with it. That's a minus sign. Shame, shame, shame on you. Well, the wrong one. Erased. There we go. Okay. Back to the drawing board. That was a minus. Because you see down here we were subtracting ce to the 4x times y. So that was a minus there. And so this is a minus ce to the 4x, close parentheses, and that's equal to, now I'm going to factor out the 2 here, 2 times, I'm going to reverse the order and make it 1 plus ce to the 4x. That's an x. It's an ugly x. Okay? How are we doing time? Oh, yeah. Okay. So now all we have to do is divide both sides by this, and that gives us y is equal to 2 times, ooh, that's ugly, 1 plus ce to the 4x over 1 minus ce to the 4x. I could have put parentheses there rather than brackets, but since I put a bracket on that side. All right, I think that's the answer that I got. Is that the answer that they got in the back in the book? They didn't put the bracket around it. They just said y is equal to 2 times 1 plus ce to the 4x over 2 times, over 1 minus ce to the 4x. Okay? And that's a perfectly correct and legitimate answer, except we've lost some values here. Because up here, if you look at this, you would see when y plus 2 or y minus 2 here was equal to 0, either one of those, then dy would be 0, dy dx would be 0. So those are two solutions here. Y equal plus 2, y equal minus 2 will both make this 0, and when that's 0, your derivative is 0. And you will not get those down here. You cannot put a y equal, this will never give you a y is equal to 0. And the reason is, the only way that could be 0 is either if 2 is 0, which of course it isn't, or 1 plus ce to the 4x is equal to 0. No, I'm sorry. I said that wrong. Y is equal to either plus 2 or minus 2. Okay. And I won't go into all of it, but I don't think you'll ever produce those here. And the reason you won't is because you divided by this. See, originally this was not a problem, y being plus or minus 2. It's only when you divided by that it became a problem. So your answer, everything we did here disallows y is equal to plus or minus 2. However, that wasn't disallowed in your original equation. So those are your lost values there. And I think they talk about this here. Now, if we factor the right-hand side of the differential equation as that, we see that the critical points, y is equal plus 2 or minus 2, are two constant equilibrium solutions. However, you'll never get those from these curves here. These will be the curves in between those values, but they won't be the value. Okay? Now, there is something else said here. Y, they say, can't equal the negative 2. That's a singular solution. Okay, I see what they're saying. Y is equal to plus 2 could come out of this. I said I didn't think it could, but it could. Because well, you have to go through and do a pretty thorough analysis of this. That is possible. For y equal to 2, that means this thing is equal to 1, because you could divide both sides by that, and this thing can equal 1. But for y equal negative 2, this would be a negative 1 on this side, and I don't think there's any way in the world you can make this turn out to be a negative 1. Okay? I'm not going to do it or try to do it now, but it is. So y is equal to minus 2 is the only singular solution. It cannot be chosen for any parameter for c, whereas y is equal to 2 could be chosen. Choose c equal to 0. C equals 0 here and here. That would be 1 over 1. Y is equal to 2. That is the solution. Try to come up with a c equal to anything that makes this a minus 1, and you're not going to do it. So one of these was not lost. The y is equal to 2 is in your family of solutions. The y is equal to minus 2 will not be in your family of solutions. Okay? But it is still a solution for your initial. So that's the one you lost. Okay? Now, they don't show a graphic of it. I sort of wish they did. Because I think in that case, and I'm just doing from the top of my head, because they called these both equilibrium solutions, I think you'll find that y is equal to 2 would be one that is a stable, and y is equal to minus 2 would not be. That would be diverging around minus 2 or semi-stable, but it would not be legitimate. Okay? It's definitely going to be semi-stable. As the first one's stable, then it's approaching 2 in the long run. It's going away from minus 2 in the long run. Okay. So, but they didn't draw a picture, so I don't want to do any more arm waving. Okay. All right. So, do we have time? Yeah, let's at least get started on example 4. Any questions on this one before I erase it? Okay. So let me clear the screen, all the drawings, and don't let me go past 45, because 10:45, because I have another class starting at 11. Okay. Here's example 4. Solve this initial value problem. Right off the top, I'm going to say I don't think we're going to finish this, just looking at it, but let's see if we can. You got e to the 2y minus y, and that minus y is on the same line with the e, not on the same one with the 2y, times cosine x. This is looking less and less likely we're going to finish it in the short time we have. But let's see. So let's at least get started. dy dx okay, is equal to, is this as painful for you to watch as it is for me to write, e to the y started to get an answer for that, but they chickened out. Okay, times sine 2x. This is looking worse all the time, isn't it? I think they've thrown everything into this problem, haven't they? It is an initial value problem, and that's y of 0 is equal to 0. So you have an initial value for y of 0 when x is 0. Okay. Now, what I'm going to do several things at once, and I hope you all are used to this now. I'm going to write this in differential form, meaning putting the dx over on this side. Okay? Now, in doing that, I want my y's over here, which means I'm going to divide the e to the y into this term over here, and divide the cosine into this term over here. Remember, the dx is already over here. So is it okay for me to do all that at once so I don't have to write as much? So let's get all the y's over here. So your functional values of y is e to the 2y minus y divided by e to the y and then you just have your dy here because we moved the dx to the other side, and this is equal to, you moved your dy over, the e to the y over here, so it's gone, and you have just sine of 2x over cosine of x and then you have your dx. Dx's always come up weird, don't they? Okay, you got all the x's on the left-hand side, that's sine 2x over cosine 2x, dx, and all the y's on the other side, e to the 2y minus y over e to the y dy. Now, let's first simplify things as much as we can. Let's break this into a ratio here minus a ratio here. Y'all okay with that? E to the 2y over e to the y is just simply going to be e to the y. You buy that? E to the 2y over e to the y is going to be e to the y. Because this is e to the y plus y, which is e to the y over e to the y. You only have e to the y left. But here we still have the minus y. Actually, I'm going to write that a slightly different way. Minus y e to the minus y. Can I write it like this? Now, that doesn't need to be up in the air. It just wound up there by mistake. Okay? And this is times the dy. I think we simplified that a little bit. Okay. On this side, just a quick reminder. Does anyone remember the double angle formula for sine? Sine of 2x is the same as, anyone remember? 2 times the sine of x times the cosine of x. Of course you remember that, don't you, Dawson? I know your trig teacher pretty well. It was me, okay? Wasn't it? Okay? Remember your your sum angle formula? Sine of x plus y was sine x cosine y plus sine cosine plus sine. Let me start over. Sine of a plus b, so I won't get the x's involved. Sine of a plus b was sine a cosine b plus cosine b sine a. No, I said it backwards. sine B's cosine A. Yeah, that's what I meant to say. And if A and B were the same, then the cosine sine A, cosine A are the same, and you have two of them. So that's where that comes from. And since that comes from that way, we can wipe out a cosine X. We've already wiped this out. So that makes the right-hand side a lot easier to deal with. I think we can manage it. Okay? And so that comes up to be 2 times sine X dx. That time it didn't come up quite as badly. Okay. All right. I think we're at the point where we integrate both sides. I'm going to take the 2 out of the integral on this side. Okay. Now what's the antiderivative of e to the y? Easy question. Antiderivative of e to the y is?
E to the y.
E to the y, my favorite function of all time because it's easy to differentiate and integrate. Okay, easy is over with now. Now we have the integral of y e to the minus y. Does anyone remember a technique that works on this one?
Product rule.
It's close to it. It's not partial fractions. It's integrations by parts. It almost sounds the same, but it's different. Okay? And with integration by parts, what you do, and we're running out of time, we choose one u that we hope when we differentiate it's going to get simpler, and one dv that we hope when we integrate it, it's going to stay no worse than it was before. So in this case, I would let the u equal y, and the dv to equal to, and you know what? I think I want to pull that minus sign back in. Make it minus e to the minus y. But you put the d's with each other, so put the dy with this one, because that's the dv one. Okay? Then you integrate this one, differentiate this one, and you got du is equal to dy, right? I'm doing too much talking now because we're running out of time. And when you integrate this one, you get v is equal to, and you never put constants in here, okay? And that will just be, I'm pretty sure, e to the minus y, isn't it? Okay? Now remember, since I pulled that back in, I'm going to put this as a plus and put the minus back in here. Okay? Okay, let's check and see. Yeah. du is equal to dy. And if you differentiate this, you get dv is equal to e to the minus y times a minus 1. So that's why I pulled it back in, times dy. Okay, well, what does your integration by parts, you got me saying it wrong, Dawson. Okay, integration by parts say it's the u times v, which is y e to the minus y. That's u times v minus the bottom line, and that's this one. That would be the integral of e to the minus y dy. Okay? Now, this will be y e to the minus y and again, I would move this minus sign back inside, and you see that is simply, now that becomes a plus out here, e to the minus y. Okay. So the left-hand side is done. It's e to the y plus y to the minus y plus e to the minus y. And that's equal to, what's the antiderivative of sine? Somebody. Minus cosine. And then somewhere out here you have a plus c. And since we've gone out of time, what we'll do next time is figure out what the c is. Okay? And let me go on and bring this one down because I left it hanging up there. E to the y plus this mess. Okay? And next time we'll figure out what the c is. Is that okay? Now, we almost finished this problem, even though it seemed really nasty, but we got right to the point of substituting. Let's make sure we got it right. E to the y plus y to the minus y plus e to the minus y is equal to minus 2 cosine x plus c. Yes, we got to equation 7 in your book, but we couldn't evaluate it because we ran out of time. So we'll start off there next time. Homework exercises in this section. Whoa, we came close to finishing. Any of the odds 1 through 21. Okay? I think you should be able to do most of those. And I think you can do most of the odds that are in the back of the book of 23 to 27. Okay? And I think you can do 29. I believe you can do either 31 or 33. I'm not sure, but I think you can do 35 and or 37. Let's hang off and we'll look at the rest of those next time. Okay? Any questions? At all? All right. Remind me that we'll pick up here next time. We only have a little bit more to go and we will be through. So unless there's more questions, I'm going to stop the sharing because I don't like to share. Okay? So that's over with. And that means I'll stop the recording. So take care. We'll see you on Thursday. Okay?
Yes, sir.
All right.
Yes, sir.
Bye-bye. Mm.